All right. Okay, welcome back, everybody. Today we're going to be doing section 13.4. This is actually the last section in chapter 13, and it's all about motion in space. The good news is that it is not nearly as long as the last lecture. So I'll get started. We'll do a quick overview and then get you on your way. Okay, so motion in space. We're going to talk about velocity, speed, and acceleration, briefly talk about Newton's second law of motion, and then we'll finish up with the tangential and normal components of acceleration. One quick note, velocity, speed, and acceleration, it really is just what you kind of remember from Calculus 1, except now it's in higher dimensions. So if you can remember the differential and integral relationship between velocity and acceleration and position, I should say, then it's kind of an extension of that. So it's not too much new stuff. One thing is, yeah, we're just going to touch on some of the basic formulas. You will expound upon these ideas and these formulas in great detail in a physics course. Also, the stuff that we talk about at the end of this course, you'll explore much more in physics courses. So this is not meant to be an exhaustive discussion of velocity, speed, and acceleration. It's more like, hey, now that we have some, mathematical calculus tools, let's use them a little bit. This section of the book actually has more content that we will not be covering, in particular projectile motion, and oh yeah, and in particular Kepler's laws of planetary motion. So you should read it. Just open the book, read those subsections, and yeah, if you ever wanted to literally see how you derive Kepler's laws of motion, it's in this section of the book. We won't have time to cover it though, so I leave that to you and to your physics professors later on. All right, so let's start with a definition. So we're going to begin with a position vector of, say, a particle moving through space. It's given by the vector function r of t. Then its velocity vector is simply the derivative, which we talked about before, right? So you take the derivative of position, you get the velocity. The speed of the particle is just the length of the velocity vector. So one thing to keep in mind, or just to remember, is that velocity is a vector. It's got magnitude and direction, but speed is just magnitude. So speed is, it's just how fast, not in which direction. A good example is the speedometer in your car. So if you're ever driving around and you're like looking at the speedometer, that's just telling you how fast you're going. It's not telling you what direction you're going in. And in fact, if you were to hit reverse, the speedometer will just tell you how fast you're reversing. It won't actually indicate that you're going backward, right? Okay. Um, Now well, we lost my train of thought. Sorry. Speed of the particle is this. Since oh yeah. And what is this? This is just the change in arc length with respect to time, ds dt right there. The acceleration is just the second derivative, so it's the derivative of the velocity vector, which is the second derivative of the position vector. So everything that you remember from Calc 1 in this regard is basically the same, except now we can talk about higher dimensions. So let's start with a simple example, and this is one that I do want you to try on your own. So find the velocity, the speed, and the acceleration of a particle whose trajectory is given by this vector function here, right? So first, just ponder for a moment how you're going to do it. Right? Now say something out loud about how you will proceed. It could even just be the formula. Remember, you don't have to talk to anybody in particular. It could be the wall, it could be your dog, your cat, whatever. Just say something out loud to give your brain that feedback. Right, and now go ahead and calculate it. See what you get. Find the velocity, the speed, and the acceleration, and we'll do it together in just a moment. All right, here we go. So we have the position vector. So to find the velocity vector, we just differentiate it with respect to t. And then to find the speed, we'll take the length of that vector. And then to find the acceleration, we just need to differentiate the velocity vector again. So this is what we get from all this stuff. So velocity vector is just the position differentiated using just basic single variable differentiation rules here, product rule right here, and then we find the length of that vector just by using the distance formula, or that formula for length of a vector. And then for the acceleration, we differentiate the velocity vector again, or I should say we differentiate the velocity vector, we differentiate the position vector again, and we get this for the acceleration. And that's it. That's the basics of it. So not too bad. All right, next example. This is a fun one. A spaceship starts at an initial position given by this position vector, and it's got an initial velocity given by this velocity vector here. Its acceleration is given by this vector, and the question is, what's its velocity and its position at any time t? So this is one I also want you to try on your own. So ponder it for a minute, read it a couple of times in your head. Okay, and then say something out loud about how you're going to begin. So how would you start this problem? Maybe take a look at what you've got and say out loud to yourself what you've got to work with. All right, now try to calculate it on your own, and then we will do it together in just a minute. All right, so let's do this one together. So let's see, we've got an initial position, and we've got an initial velocity, and we have an acceleration vector that gives us the acceleration at any time t. So, okay, so this is a situation where if we want to recover the velocity and position vectors, we're going to have to integrate the acceleration vector. So we can integrate the acceleration vector to get the velocity vector, and then we can use this initial condition to find an explicit form of the velocity vector. And then we can continue. We can integrate the velocity vector that we get, and then we'll be able to get a position vector and then use this initial condition. So that's what we're going to do. All right, so first thing we need to do is integrate our acceleration vector. Acceleration is given by this right here. Here I've written it in terms of the basis vectors, the standard basis vectors, ijk. And then you can integrate it just like you remember from Calc 2. So just do a simple single variable integration. That's the antiderivative of 4t. That's the antiderivative of 6t. That's the antiderivative of 1. And if you remember from Calc 2, one very, very important point is if you have an indefinite integral, you have to include the plus c. The plus c is important. You got to remember the plus c, otherwise your results may not be valid. Generally speaking, I know I said this earlier in a different lecture, but just remember that an indefinite integral really is representing a family of functions, not just a single function. So this plus c is accounting for all of the possible all of the possible results that you could get from this anti-differentiation process. And this is why you need an initial condition. So we basically we have a family of potential velocity vectors, right? So v of t is equal to this, but now we need to solve for c. And that's what this initial condition is all about. The initial condition will basically tell you what value of c you have. It'll take that family of functions and just lock it into a single function. So here we go. Here's our initial condition on v. So we plug that in for the formula we found for v, and we'll be able to solve for c. So once we go through all of this, here we go. So we're plugging in, so this is equal to v0, which means that this has to be equal to this. And then we can calculate from that c is equal to I minus j plus k. So that's like the initial velocity vector, you could say, or not the initial velocity vector. This is the vector that is c. Okay, now we can proceed. So we've got v of t, we solved for c. Now I'm just going to combine like terms. So combine things in terms of the standard basis vectors I, j, k, and now we actually have a proper vector for our velocity. Now we have a velocity function, right? We have a velocity function. Continuing, we're going to do the same process to this velocity function, and we're going to anti-differentiate it again using the same process we did as before. And in this case, we're going to end up with another unknown vector that we have to solve for using the initial condition we had on the position. So simple anti-differentiation, this should be like, a breath of relief when you see it. Again, this is one of the reasons we love polynomials, because polynomials yield very easily to the power rule. So you just use the power rule for antiderivatives 3 times, and then we've got this unknown vector d. Right, so that is the general solution. This is the general solution for our position function. Now we plug in our initial condition for our position, that the initial position vector is 1, 0, 0, and then we get this, and this lets us solve for D. There we go. So we're plugging 0 in for T. We get this, and then we get that this is equal to this, and then from this we can see immediately that I is equal to D, or D is equal to I, if you will. So that's our exact value of D. Now we can substitute that into our general formula for the position vector and rewrite the whole thing like so. So that's the position vector. That's the position vector of the particle that has these stipulations here. Or sorry, the spaceship. That's the position vector of the spaceship. All right, so that one. Okay, moving along. Now let's talk briefly about Newton's second law of motion. So this is the one that everybody knows and loves. You probably heard about it if you took a high school physics class, or maybe just heard it anywhere out in the wild. Um, it's the F equals ma formula, right? So here's what it is. If at any time t, a force F of t acts on an object of mass m, producing an acceleration a of t, then this relationship holds. The force is equal to mass times acceleration. Good old F equals ma, right? So now we're going to use this formula to do this example here. So this is a fun one. And again, this is one I want you to try on your own before we do it together. And it says this: an object with mass m that moves in a circular path with constant angular speed omega has a position vector, radius, given by this formula here. So that's the position vector of this object that's moving in a circular path. Oop, this way. There we go. And my task for you is find the force acting on the object and show that it is directed at the origin. All right, so here's one. Start by just looking at it, thinking about it for a moment, reading it in your head a couple of times. Okay, now say something out loud to yourself, to your friend, your group mates, to your hand, to whatever you want. Give your brain that feedback. All right, and now try to work it out on your own, and we'll do it together in just a moment. All right, here we go. So let me think about this. You've got an object with mass m, it's moving in a circular path, constant angular speed, omega, and it has this position vector. So the first thing is this position vector makes sense because this is basically the formula for a circle, right? This is the parameterization of a circle, right? Cosine and sine. And then a is basically the radius in this case. Yeah, a is basically the radius of that circle. Yeah. All right. So if we want to find the force, we know F equals ma. So we're going to have to differentiate twice, right? We have the position. So if we want the acceleration, we need two derivatives. Here we go. Here's our two derivatives. So this is the acceleration vector. Yes, yes. Oh yeah, another thing I should mention here. You may not remember this, but this is a good time to remind you. Angular speed is d theta dt. So the way that I remember this is that angular speed is literally, it's literally change in the angle versus change in time. So it's basically how fast the angle is changing, aka angular speed. That's the way I always remember it, angular speed, right? Now we have our acceleration vector here. So then we can plug this into our formula. F equals ma. Here's our acceleration vector. Here's our mass m. And then now we can basically simplify some things. So what did I do here? It looks like I pulled out the coefficient of omega squared, and looks like I pulled out this -1 coefficient and rewrote it like so. So one of the cool things about this result is that this actually is the original position vector of our particle, or our object. There you go. So that means that F is equal to this right here, negative mass times omega squared times r of t. All right. So here's the force we were looking for. That's the first part of the question. The second part of the question is show that it's pointing inward toward the center of the circle. Well, since the vector is negative, that means it points in the direction opposite the radius vector. So let's take a note of this real quick. Grab this pen here. This is the radius vector. This is basically saying where you are on the circle, right? So, or sorry, let me, yeah, it's basically this. So this right here is r of t. It's my finger as you go around the circle. That's what r of t is. Now, because you have this negative coefficient in the front, it's literally the opposite of r of t. So it's pointing inward, literally pointing toward the center of the circle. And that's it right there. So negative r of t is this. R of t, sorry, it's messy. And that's what all these other blue arrows are showing you, that in this case, the force is directed inward toward the center of the circle, and this is what we call centripetal force, or the center-seeking force. So this is how you define it. All right, moving on here. Next, let's talk about tangential and normal components of acceleration. So the theme here, or maybe the moral here, is that when you're studying motion, it's often useful to break up the acceleration of a particle into two components. The one that's in the direction of the tangent vector, so acceleration in the direction of the tangent, and one that's in the direction of the normal vector, which is basically where the object is turning, right? So you can decompose acceleration into these two components. Yeah, acceleration drives the particle in the direction of the tangent, as well as the direction given by the curvature. Because if you're basically turning as you move, then there's a normal component of the acceleration, and a component that's not just in the direction of the tangent. Um, so one thing to note here that I'll point out again when we derive the formula, this means that the vector for acceleration lies between the unit tangent vector and the normal vector. So in other words, the vector for acceleration lies in the osculating plane. And that was something we talked about in the previous section, right? The osculating plane. So in other words, your acceleration vector lies in that plane, the osculating plane. And we're going to see that in just a moment. Okay, so here's how we derive this. We're going to derive these components directly using what we already know about derivatives and then from the previous sections. So here's how we start. We're going to let regular V be the length of the velocity vector. So in other words, the speed of the particle. So whenever you see this little non-bold v, it's the speed, all right? Just the speed. Then what we can do is we can rewrite our unit tangent vector like so. So if you remember the formula for the unit tangent vector, it was the tangent vector divided by its length, right? But the tangent vector here is what we're calling the velocity vector v. And r prime, or there you go, r prime is v again. So this is basically the length of the velocity vector, which is the speed. So we can re-express the unit tangent vector as the velocity vector divided by its speed. Right, so that's the first thing to kind of wrap your head around. So maybe just stare at this for a minute and think about what that first equation is telling us. All right, now just by some simple algebra, basically multiplying both sides by v, we get that the velocity vector is equal to the speed times the unit tangent vector. And that makes a lot of sense if you think about it, right? So what is our velocity vector? Well, it's basically the unit tangent vector scaled by the speed at which you're traveling. That's what it's saying right there. So take your unit tangent vector and stretch it by however fast you're traveling. That's what's going on here. Right, so now we're going to proceed again. We're going to differentiate both sides of this equation, and we're going to get a formula for acceleration. We're differentiating with respect to t. Remember that regular v and bold t are both functions of the parameter, little t. So that means we have to use the product rule. We have a product of two functions of, we'll say time. Little t, we'll say it's time, for example. So when we do the derivative, when we compute the derivative and we differentiate this vector, we're going to get this formula. Acceleration is v prime t plus v t prime. So here is a formula for the acceleration right here. Right. Now we're going to bring some other things into it and recall some stuff that we learned in the previous section, that really long one. So remember from section 13.3, the curvature formula is given by this right here. So remember, kappa is the length of t, capital T prime over the length of r prime. Well, remember, r prime is just v, right? R prime is just v. So we're going to take the size of v, but v is already just the size of r prime. So we end up getting this with just a little bit of algebra. So in other words, the length of capital T prime is equal to kappa times v. That's the first thing we're going to need. Next, remember that the normal vector n is given by t prime divided by the length of t prime to make it unital, right? So using this formula, we can actually solve for t prime. And so we get that t prime is equal to this times this. Let me kind of highlight it there. There you go. So t prime is equal to length of t prime times n. But we just calculated up here that the length of t prime is kv. So now we get this formula right here, that t prime, capital T prime, is equal to this. All right. Now what we're going to do is we're going to take these results and we're going to substitute them back into our previous formula. So let me just remind you, it's right here. V prime t, v t prime. Now we're going to substitute these values in and we get this. That acceleration is v prime t plus kv squared n. There we go. Or we're going to rewrite these like so. A sub capital T and A sub capital N, and those are our tangential and normal components. Let's see a picture. Okay, so here's a picture of the scenario. Let me describe it a little bit. A sub T, that's what we call the tangential component of acceleration. And it makes sense. This is basically the component that's in the direction of the tangent vector, right? So we're taking the unit tangent vector and then scaling it by A sub capital T. And then A sub capital N is the component of acceleration that's in the direction of the normal vector, which is basically where the curve is turning. So pictorially, it looks like this. Maybe I'll zoom in a tiny bit. Here we go. So let me point out a couple of things here. Here's our tangent vector. Here's the curve. That's like our trajectory, right? Here's the tangent vector. So the acceleration vector is going to be between the tangent vector and the normal vector, which you can see here. And so what we're really finding is we're decomposing the acceleration vector, which is here, into its two orthogonal components. One that's in the direction of the tangent vector, sorry, right here, and then one that's in the direction of the normal vector, right here. So those lengths are what we call the tangential and normal components of acceleration. So if you ever get confused, you can always look back at this. Now, one thing that's interesting, because I mentioned it a couple of slides ago, but note that this formula here, the binormal vector is absent from this equation. So that means that the acceleration vector lies strictly in the osculating plane. So it's not just something that you can make up or not something that needs to be, well, you don't have to rely on intuition for that. It actually shows up in the calculations that the acceleration must lie in the osculating plane because the formula for acceleration does not involve the binormal vector at all. Right. So let's peel these things off and look at them specifically. So the component, the tangential component of acceleration is v prime. So it's the derivative of speed. And the normal component is kappa v squared. So it's the curvature times v squared. So the tangential component is really just the change in speed, which kind of makes sense, right? Now the normal component is the curvature times the speed squared. And there's a good analogy in the book, so I quoted it right here. It says this. It says, think of a passenger in a car. So put yourself in a car for a moment. If you have a sharp turn in the road, that means there's a large curvature. So the component of acceleration that's perpendicular to the motion is large. So imagine doing like a very tight turn in a car, right? Well, if you're doing a really tight turn, the curvature is large. And so that means that the normal component is going to be large, the normal component of acceleration. Similarly, if you have a large speed, so if you have a large speed, then this component is going to be very large as well. The speed itself, right? V instead of V prime. So there's a little bit of intuition for why these formulas are appearing the way that they do. Okay, now here's the fun part, or maybe I'll say the tedious part. Kind of depends on your perspective. Like we saw before, So like we saw in the previous section, sometimes it's easier to have these components in terms of something simpler, like the position function itself, right? So rather than have to write everything in terms of curvature and like the derivative of the speed and so on, it'd be really nice if we could compute this if we just knew the position vector, right? Like it would be nice if we knew that. So we're going to derive formulas for these things. Here's how we start. So this is kind of clever, so watch it here. If we dot the velocity and acceleration vectors and use those formulas that we have, we can do a little bit of algebraic massage and we get a nice formula here. So here we go. This dot this, remember the dot product is distributive, so you can distribute this factor to both of these terms and you get this, right? But remember, t dot t is t is a unit vector, right? And if you dot a unit vector with itself, well, they're pointed in the same direction, so the angle between them is 0, and cosine of 0 is 1. So t dot t is just 1. And also remember that t and n are orthogonal to each other. T and n are perpendicular, so that means their dot product is 0. So you get 0 right there. This entire term gets wiped out, and you're left with v dot a equals little v times v prime. So if we solve this for v prime right here, we get a formula for the acceleration, the component of acceleration in the direction of the tangent vector. There we go. This. Okay, so now we made a little bit of progress. Let's continue. Now, v dot a, if you remember, v is just r prime, and a is r double prime. So we can rewrite the top as r prime dot r double prime. And then remember that v, well, v is just the speed, so it's the length of the velocity vector down here. So r prime of t, you take the length. And so now we actually have a formula for the tangential component that is strictly in terms of the position vector and its derivatives. Or I should just say the derivatives of the position vector, first and second derivatives. So that's handy because basically if you start with a position function, differentiate it once, differentiate it twice, and then you can find the tangential component of acceleration using this formula. All right, now let's find one for the normal component. So this one, if you remember, we went through and computed all these different formulas for curvature, right? Well, now we're going to use one. So we're going to use it right here. So this is the formula for curvature. Let me highlight it a bit. Kappa, and you're welcome to refer back to section 13.3 to see, but this is the formula for kappa right here. And then v squared is just length of r prime squared, right next to it. Oop, there we go. That. Well, if we've got 2 factors of length of r prime here and 3 factors of length of r prime down here, we can cancel 2 of them and we're just left with 1 of them. So this is kind of a cute result. So altogether, cutely, this is the formula for the tangential component, and this is the formula for the normal component. Very similar, very similar. So this one's just r prime dot r double prime. This one's r prime cross r double prime, and then take the length. And then they're both divided by the length of r prime. Uh, just again, something I'll say, you do not need to memorize these formulas. I will give you these formulas on in the exam. Again, I'm not a big fan of memorization, and the truth is that it's just very easy to mix these formulas up. They're very similar. The operations are very similar, and it's just, it's a shame to basically accidentally put a cross here because you happen to forget that it's supposed to be a dot, right? So I will give you these formulas. What's more important is that you think about how we derived the formulas and then to make intuitive sense of why they're working, right? And then to know that a formula does exist. So the idea is if you ever had to calculate the tangential and normal components of acceleration, you should know, oh wait, there's formulas for both of those that only depend on like the first 2 derivatives of the position. What are they? It's like this times this or this cross this. That's a good place to be. That's a good place to be. All right. If you, I'll actually, let me add this. If you do happen to memorize them, that's not a bad thing. So if you do memorize them, more power to you. Congratulations. Good job. So don't feel like, it's bad to memorize them or anything. All right. So here's one that I want you to try on your own. All right. So find the tangential and normal components of acceleration for a particle whose trajectory is given by this vector function here. So think about it for a moment. How are you going to start it? All right, now say something out loud to yourself about how you're going to start it. Right, and then try to compute it yourself, and we will do it together in just a moment. All right, here we go. Well, if I need to find these, the first thing I know, if I need to find anything related to acceleration, the first thing I need is two derivatives, first derivative, second derivative. So let's start with that. Then I'm also going to need speed because I know that it's directly related to the speed in some way. So we're also going to find the speed. Here we go. Here's r prime. Again, this is why we love polynomials, because they yield instantly to the power rule and it makes life very easy. So there we go. Differentiate that again. And then now we can also find the length of r prime just by using the distance formula, or that formula for length of a vector. And now we have almost everything we need. Well, we have what we need to get started. So let's do the tangential component first. Tangential component is r prime dot r double prime. We just computed those two vectors here and here. So we dot them together, we get this. And so this is a formula for the tangential component of acceleration. Not too bad, right? All right, next, if we want to do the normal component, we need to compute a cross product. So we're going to use our determinant formula again. So we're going to take r prime and cross it with r double prime. Here's the determinant formula, and I'll let you work this out on your own. Hopefully you did it already, or at least started it. This is what you get when you compute that cross product. So then the last thing we need to do is compute the length of the cross product. And once we have that, we're done. So here's the formula for the normal component of acceleration. Here's the formula for the length of that cross product vector right there. And then everything simplifies down to this. And that's what we've got right there. And I think, let me check something. Do I have a, I don't have a Mathematica example here, but that's all right. Not everything needs a mathematical example. So on that note, I'll just say, let's play. Let's play. So this section's not too bad. I feel like it's pretty gentle. It's nice that it's a little bit shorter. I'm excited to work with you all on the activity for these. I think that's just the most fun, when you just get to get your hands dirty and dig in. But I'll stop rambling here, and I will see you all next time.